Okay, good morning, class. Hope you are staying warm and driving safely. We'll be starting this lecture due to the cancellation of the class on Thursday, February 9th. So we'll continue our discussion in statistics. Okay, so let's start. So statistics is kind of a branch of probability theory, or it's an application of the probability theory. And as we discussed on Tuesday, well, statistics mainly about drawing conclusion about a population. So you want to draw conclusion about a certain population. Okay. But due to various reasons, sometimes resource-wise, sometimes the population itself doesn't physically exist. So we have to turn to some other um, means to find or to draw this conclusion. That is based on what we call sampling. Based on the data obtained through sampling. So sampling means we're selecting a special group of individuals from the population. Hopefully this special group of individual can somehow represent the typical behavior of a population, such that if we make some conclusion based on the sample data, they can be naturally extended, can be applied to the entire population as well. So this is sort of the gist of statistics. And of course, we're in this chapter, we're going to discuss some of the basic methods and ideas in statistics that will be useful for our future discussion related to quality, control charts, those type of things. And we discussed, well, in terms of statistics, there are two things or two main tasks. One is called estimation or parameter estimation. That means there's some special quantity I want to estimate from this population. For instance, the fraction of number of people that will vote for certain candidates. Okay. The average SAT scores of all students in America, all those are the special quantities, in other words, parameters. Okay. This is one task of statistics. The other is called hypothesis testing. Hypothesis testing is mainly carried out when we would like to draw some comparison of a certain parameter against a reference value or against another sample. Okay. You can compare two options, two players, which one is better, or you can compare the specification of a certain product against a hard requirement. Does it satisfy this requirement or not? Okay. These are the two things that we may see in statistics. So the simple way or the normal way to look at statistics is to borrow the ideas from probability theory like we discussed last time. So this is the storyline. We're going to construct a sample. As I mentioned, well, it's easy to say we have a sample, but there's a lot of science and engineering between how to draw, how to select a sample. Let's skip that for now. Let's assume we have a sample, and the sample has n items or n individuals or n data points. Okay. So like you have a spreadsheet, you fill in numbers in it. It can be 100, it can be 200, it can be maybe 10, 15, or 20, depending on how many times or how many items you have selected into the sample. Now, since drawing or selecting an individual from a population depends on how you do it and how you make the selection, it's sort of a random experiment. Okay, so we can see selecting an individual into the sample is a random experiment. If it's a random experiment, and if our interest is to do certain calculation on a certain quantity or measurement, we can naturally formulate or define a random variable x to denote the data associated with this individual in the sample. And since we have a total of n individuals, we're going to have n random variables, and we'll use x1, x2, all the way to xn to represent the n data points in the sample. They are all random variables. It's like you draw, all n of them can be different from each other. And if I draw a sample, someone else draw the sample from the same population, maybe the two samples are different. So there is some randomness in that. Every individual in the sample is a random experiment and will lead to a random variable x. Moreover, we're going to assume in this particular course that this individuals, all this n random variables, x1, x2 up to xn, are IID. And we discussed what IID represent last time. It means they are independent, and identically distributed. This is what IID represent. Independent and identically distributed. And when we talk about this identically distributed, meaning they all have the same distribution, and that distribution is sometimes called the population distribution. So because they're drawing from the same population, of course this follows some distribution defined by the population. This is called population distribution. Now, after we draw the data, we usually do some calculations. And from your previous experience, the very usual calculation we do is to take average, right? You perform a certain experiment from your physics class or from your circuit class. Well, you do it 5 times or 10 times, then you take the average and report the average to your instructor, or include that in your lab report. So the average, since it's so commonly used, we give it a new name. We use the notation x bar to represent it. And a way to define it is easy. You just have to add up everyone and divide the summation into the total number of data points they have. And since all these xi's are random variables, all of them are random variables, this x bar should also be a random variable. You perform this experiment, you return a certain number. Another group of people perform the same experiment, taking the average. Maybe the average will be different. So this x bar, this average, is also a random variable. And we give it a special name. We call this guy sample mean. And of course, literally it means the mean or the average of the sample data. So keep in mind this is also a random variable. Right? Okay. So the sample mean will give you, well, where the center of the data is. And also we want to know, well, what about the variability? Because for population we want to know the average, the center, and we also want to know, the scattering or the variance included. So include this notation s squared, lowercase s, and it's defined as the summation I from 1 to n. So add up the distance from each data point to the center of the sample, x bar, square them, and divide them into, not n this time, but n minus 1. N minus 1. And this special quantity, s squared, is called sample variance. So this is the variance from the sample. And of course we can take the square root of it. So if I take the square root of this guy, where I from 1 to n, divide this into n minus 1. This guy is called sample standard deviation. Okay, this is called sample standard deviation. Now, what we usually want to do, as we mentioned earlier, is to draw a conclusion about the population based on the data from the sample. So since we have now the sample mean and sample variance and sample standard deviation, maybe they can be used to help us estimate the population mean, the population variance, and the population standard deviation. Right? This is what we are trying to do. And exactly how do we define those population mean, population parameter? Well, since we have defined our population distribution, is if you draw a sample of or individual item from the population, the distribution of that particular experiment. So the population distribution will certainly give us the following. So based on the population distribution we discussed earlier, we define population mean. We use mu to denote it. Of course, it should be equal to the expectation of x1, the expectation of x2, the expectation, or the mean of all the xi's, because they follow the same distribution, population distribution. And similarly, population variance is denoted as sigma square and defined as the variance of any of the xi's. Since they follow the same distribution, they will have the same mean, they will have the same variance. And then in terms of estimation or parameter estimation, what we typically do is we'll use sample mean to estimate population mean. Okay. And we'll use sample variance to estimate population variance. And we'll use sample standard deviation to estimate population standard deviation. And mathematically, it's possible to prove that these estimations are unbiased. I mentioned about this concept during Tuesday's lecture. They're called unbiased. Mathematically, this is what we can how we can define it. Now, the goal is to estimate population mean, and you're using sample mean. But sample mean itself is, as we mentioned, it's a random variable. So I have a sample mean, it can be something. You have a sample mean, it can be something. But the average, the mean of the sample mean is equal to mu. And mathematically, this is true. We can prove this, and it can be very naturally proved based on the probability theory, because each one of, I'll use a different color, because each one of them has mean equal to mu, right? Each one of them has mean equal to mu. So of course, you add everything on top will be n mu's on top, and divide it into n will give you mu. This is very natural. What is not very natural is about the sample variance and sample standard deviation. Okay. When we define them, I mentioned, well, if we look at this denominator n minus 1, someone may question why would we don't use n, the sample size, but n minus 1. It turns out if we use n minus 1, then we can prove mathematically that the population variance, which is the quantity we're trying to estimate, happens to be the variance, happens to be the mean of the sample variance, because the sample variance itself, it's a random variable. Xi is a random variable, x bar is a random variable, so x squared is also a random variable. I calculate something, that's one number. You calculate a sample variance, could be another number, but the mean of this random variable happens to be the true parameter you're trying to estimate, and similar for the standard deviation as well. Okay. When these type of things happens, okay, that the average or the mean of your statistic is equal to the true parameter you're trying to estimate, they're called unbiased. Okay, so unbiased is defined such that the true parameter of the population you're trying to estimate is equal to the mean of the statistic. Okay. And in this case, the statistic for the first line here will be x bar, your sample mean, and the true parameter is their population mean. For the second line right here, the parameter you're trying to estimate will be the population variance, and the statistic you're trying to use is the sample variance. So this is what we call unbiased. So this is what we have started last time. Now we're going to continue our discussion, but let's keep in mind, reinforce our memory that we're looking at a few new random variables: sample mean, sample variance, sample standard deviation. They're all random variables, and they are all defined as a result of the data from a sample. So sometimes we'll introduce a concept called sampling distribution of a statistics of a statistic. And we measure a statistic just basically any random variable you define based on the individual in the sample. So x bar is a random variable defined based on the individual data points from the sample. S squared also is defined as a function of all these xi's, and x bar also depends on xi. So again, depends on the data. So as long as it's defined as a function of the data in the sample, we call it a statistic. A statistic is naturally a random variable. And since it comes from sample, we sometimes refer to the distribution of a statistic as the sampling distribution. Okay, so when we say this is equivalent to saying just the probability distribution of that statistic. It will be equivalent. Okay, so let's see, since they are random variables, maybe The distribution can tell us more information about where to go about in the statistics area. And we'll discuss this in the next section of the video.